have to keep the lectures also, have the lectures also ready. From that one, if we can open from that one and you can see.
Now, sir, you are ready, sir, for live.
Yeah, go ahead. Yeah.
Live now, sir.
Oh, okay. Every stage. There is some time lapse is there, I think.
Yes, sir.
Yes, sir.
Hi Manish, you have any question? Ravi, why there is a delay?
Hello, sir.
It was recorded like
So there was a question about ClO2 minus and writing Lewis dot structure for ClO2 minus. The question was, is there any triple bond between oxygen, or is there any possibility of oxygen forming triple bond? There is no triple bond in ClO2 minus, and oxygen is less likely to form a triple bond. And what you have to do here in case of ClO2 minus is simply count the valence electrons of all the three atoms plus add one electron because of negative charge. Totally it comes around 6 plus 6 plus, okay, 7 plus 1, 20 electrons it comes. Okay. Now we have identified the central atom. So then identify the central atom, and then now in case of ClO2, Cl is the central atom, and place on both sides oxygen, and use 4 electrons to make one single bond on each side with Cl and O. So we are spending 4 electrons. And now the most electronegative atoms are oxygen. And now satisfy octet of 2 oxygen atoms by adding 6 electrons on each side. So 6 plus 6, 12. Okay. And plus 2, 14 electrons are there. Now 4 electrons are left. Those 4 electrons you place one above and below middle Cl. Now all the electrons are consumed and all of them satisfy octet rule. So there is no need to evoke any double bond or triple bond. Yeah, electron affinity means, okay, adding an electron to an atom, okay, that's called electron enthalpy, okay, that also we call it as electron affinity, okay, so when we want to add an electron, we need some energy has to be spent, okay, to minimize, so when you are adding an electron, basically what happens, more electrons will be increased, okay, number of electrons will increase in the valence shell and hence it will be reduced to 4. So there will be some repulsion. To minimize the repulsion, you have to spend some energy. That is called electron affinity. For example, Cl is there. If you add an electron, okay, Cl minus, that is called electron affinity. And if you have O minus is there, you add another electron, that is called electron affinity. So addition of an electron is nothing but electron affinity.
Lecture 5 we have talk about the pointer and pointer question.
Yeah, there are several examples I have listed in the table I have provided in the hybridization concept or in VSEPR theory. Basically, I have listed all of them. I think I have given a table where I have cited examples having no lone pairs and also having several lone pairs with different geometries. For example, if we have tetrahedral geometry where 2 bonded pair and 2 lone pairs are there, or 3 bonded pairs, 1 lone pair is there. For For example, if you look into geometry 5, we have several examples, okay, having T shape or linear shape or okay, having 4 and 1. All these examples are there where you have 1 lone pair and 4 bonded pairs, 2 lone pairs and 3 bonded pairs, and 3 lone pairs and 2 bonded pairs. For example, I2 minus is there, Br2 minus. They are examples for 3 lone pairs, and geometry, diagonal bipyramidal, and the shape is linear. So all examples are given in the table. For example, if you consider CLF3, we have 3 bonded pairs are there and 2 lone pairs are there. They have T shape. And if you take S4, we have 1 lone pair and 4 bonded pairs are there. It has seesaw structure. All those things are given. The question from Manish is how to stabilize the lower oxide state of a tungsten metal. Yes, for example, if you consider 3D, 3D metals can have up to 6 coordination number, and 4D and 5D can go up to 6 or 7 or even 8. The question is how to stabilize low coordination number. In that case, what happened? In order to stabilize low coordination number, we have to go for very bulky ligands. So if you take triphenyl phosphine, very bulky ligand, okay. So if you want to have more coordination number with say 4 or 5 with palladium, it's not possible. Palladium, somehow we can manage to put 4 triphenyl phosphine surrounding it, and it assumes tetrahedral geometry. But the moment you put into the solution, okay, 1 or 2 ligands will readily dissociate to remove this cubic encumbrance.
The same question.
You see, when gallium was not discovered, it was, the position given for gallium before it was considered was already decided where it can go. So that's the reason they said since that place was black below aluminum, they called eco-aluminum means it is not there. So they gave some name, eco-aluminum, and similarly germanium was not below silicon, you see eco-silicon, that is it. What is the kind of levels we start that? Yeah. So, you see, the exact meaning is not given. If you see Eka means ek, Sanskrit word is one, it represents. That means one element that is very similar to aluminum. That's what it signifies. And for example, Eka silicon means there is one element below silicon that is very similar to germanium. That's what it says. So you see, you can come up with lot of explanation for a bulky group. Usually, when you put bulky group surrounding a metal, if the metal size is small, you cannot take more than 2, 3 or 4. So that way you can minimize the coordination number and you can have low coordination compounds. Of course, in catalysis, I have given different explanation. Same explanation holds good also. If you stabilize metal with low coordination number, that will be coordinatively unsaturated and electronically unsaturated, so that you can perform oxidative addition more readily. Without bulky group, it's difficult, Manish. You need to have a bulky group to stabilize. For example, you take, in that case, in the absence of bulky groups, what happens? If the ligands are capable of bridging, then it may go for dimeric, trimeric or polymeric forms. For example, if you take CuCl2, okay, it's not simple, it doesn't have a simple linear geometry. Copper is actually tetrahedral in nature. Also, you know, aluminum trichloride. Aluminum trichloride, if you take it, it has only 3 coordination, it's electron deficient. It assumes a dimeric structure having Al2Cl6 or BH3 becomes B2H6. In the same way, Al2Cl6 happens and also if you go for Al2F6, of course, in case of Al2F6, if you look into the structure, aluminum is surrounded by 6 having octahedral geometry. Same thing is aluminum chloride also, if you look into the solid state structure. Okay. Here in assignment, I could understand, identify the isoelectronic species. All are isoelectronic, right? Yeah, you choose anyone, you get the answer. Okay, that was a mistake. we wanted to give 1 or 2 or maybe 3 because it's a multiple choice question. We should have given uh, one which is not isoelectronic, but all are isoelectronic, no issue. Yeah, one should have been incorrect. It's not isoelectronic with the series, but it so happened that all the 4 are isoelectronic, K plus, Cl minus, and Ca2 plus, and S2 minus, all are isoelectronic. So you put any one, you will get the answer, or if you even if you don't, in case you should attempt it so that you will get the marks. Any questions? It sounds right. Please keep asking questions, or if you have really some doubts or you need to get clarified about any theme, don't hesitate to send an email to me. I shall try to answer all those questions. Okay. If not the same day, probably next day. Why dz square cannot form pi or delta bond? That's a nice question. If you just look into, this delta bond concept comes only in square planar complexes, right? In square planar complexes, if you recall, valence bond theory and hybridization theory, we are using dsp2, okay, dsp2 hybridization. The d orbital utilized in making metal to ligand bonds in square planar complexes is dx square minus y square. Other 4d orbitals are unutilized as far as metal to ligand bond formation. you consider a square planar complex, okay, and two square planar complexes eclipse to each other, okay, square planar complexes eclipse to each other, and then if you identify the position and orientation of z orbital, it will be coming like this, okay. So now, when you bring two square planar complexes together along z axis, what you see is d orbits are hitting like this. That means you can see this head-on collision that leads to the formation of sigma bond. Yeah. Not blue, orange. You see, this is two square planar complexes like this. Okay, so here we have one square planar and here we have one square planar. It's not proper. It's irritating. So much gap should not have been. Here, only option is they can form like head-on. So when one electron each are coming, you should establish a sigma bond only, because you know that sigma bond will be like this. On the other hand, in order to have a pi bonding, the orbit should be something like this, or like this, or like this. One is like this, or one is like this. One is like this, or one is like this. Okay. So next one is to have delta bond. It will be something like this. So when you bring two in this fashion, your XY will be like this. Okay. That will be delta bonding. Sure. I will show you that. This thing, right? Okay. So I can share now? Okay, sharing I have to go there. Okay.
Actually,
Google I have to share, right? Ask her how to share. How to share the slides?
Sir, there is option, sir, presentation, sir, in the middle of sign.
In this one? But,
Middle.
but I can show this one now?
Present now. You can click on present now, sir.
Yeah. Entire screen.
No, sir, window.
Wait.
Window.
Ah.
First, first do, sir, do full screen your slide, sir.
Yeah. Can they see now?
Yes, sir.
Can you see?
Yes. Yes, sir.
Okay. So you can see now two square planar complexes are put here. Why so much disturbance is there, delay? So much delay is there, it repeats after 2 minutes. Why that problem? So for example, here one square planar complex is there, here one square planar complex. In this one, dz square is here. You just see now, just see now sigma bond is established. Now if you see dxz and dyz, they are perpendicular, okay, and you can see something like this now. So this is sigma bond and the anti-bonding, okay, and now if you see dxy and dxz and dyz, they are orthogonal to each other. These two pi bonds, okay. This is pi star. So what is left is dxy. It's typically when you green like this is how the orientation is. This is delta and this is delta star anti-bonding. Okay, so this is how the bonding happens. So in this context, what happens? Dz square cannot, okay, participate in pi or delta bonding. This is delta. And this is sigma bond, this is one pi bond, this is another pi bond. Now dxy is left. Okay, it will overlap in this fashion, sideways, something like this. So this is delta bond. Okay, this is sigma, this is one pi, this is another pi, and this is delta here. This is how the orientation is. It depends on how the molecules are oriented. Hope you have understood now. Okay. Hmm. Stop sharing, right? Yeah. Is it clear? So all metal oxides are little unstable, okay, because they can readily undergo hydrolysis. Uh, and if you consider that way, see for example, alkyl metals have one electron, and alkaline earth metals have 2 electrons. Well, actually, if you just look into the stability, stability should decrease as you go down the groove in both the cases because of the difference in the size. Okay, the reactivity increases means stability decreases. So that means basically early metals, oxides will be a little bit more stable. Nevertheless, in absence of moisture. And if you consider that way, probably lithium and sodium oxides are slightly more stable compared to higher analogs. If the metal oxide has little more covalent character than ionic character, so they are more stable. So now, by looking to the charge to size ratio, and you should be able to decide, okay, if a set of metal oxides are given, which is more stable and which is least stable. Any other questions? Suraj, is it clear about metal-metal bonding? Why dz square cannot participate in pi and delta bonding? If no more questions, thank you so much. Maybe see you all in next live session. If you have any questions, list it and make a list of it and send it to me so that I can systematically make some slides to make you understand and clarify your doubts. Ravi, you can close it. Devendra, you can close it. I am closing now.
Okay, sir.